Good morning. Hope everyone's doing well. Looks like we have a warm day in store. I'll be right back while I wait for more people to join up. Waiting for a few more people. Hello? You're in the wrong class, aren't you? All right. I'm going to go ahead and get started. Well, hello. Oh, I forgot to turn my document camera on. Let me turn that on. Waiting for my document camera to turn on here. And we will get started. Thank you for showing up pretty close to on time to the 21 of you who are currently viewing. I appreciate that. Why isn't... Okay, there goes the document camera. Zoom in and autofocus. Turn the light on. All right. I guess it is a lazy Tuesday morning. Okay. All right, we are going to have a second lesson on projectile motion today. Okay. So let's just do a little review of what we learned yesterday with projectile motion. We talked about how if you have a projectile that's launched at a certain angle with a certain speed, okay, so it's launched at a certain angle with a certain speed. Part of that initial speed is vertical. We called that Vy naught. And part of that initial speed is horizontal. We called that Vx naught. Vy naught is opposite the angle, as you can see, so we're going to use the sine function. It's V naught sine of theta. Vx naught is adjacent to the angle, so we will call that Vx naught, and that's V naught cosine of theta. Okay? And then we learn the equations of projectile motion, which were delta x equals Vx naught times time. So Vx naught is calculated from this formula. And then delta y equals Vy naught times time, minus 1/2 gt squared. So notice how there is no acceleration term in the delta x equation because gravity accelerates things vertically, not horizontally. We applied these equations to two scenarios. One of the scenarios is a horizontal launch off a cliff, which looks like this. Okay, so this is the cliff. So the key idea here was that delta y is less than 0 because the projectile drops a certain distance. And then we also have Vy naught equals 0. And that is because the projectile is launched horizontally, so all of the initial speed is horizontal, none of it is vertical. Of course, as the projectile travels, it gains vertical velocity, or else it would never go down. And then the second example we learned about was firing a projectile across a level surface like this. And the key idea for this problem is that we have delta y equals 0 because the projectile starts and stops at the same elevation. Okay? So today we're going to learn two additional types of problems. Okay? So the first example that I want to do is you are egging an enemy's house. Okay? You stand, let's say, 20 meters away from the house. And throw an egg with initial speed let's say 18 meters per second at an angle of 50 degrees. Where does it hit the house? So this is the picture that you should have in your head. Here's the house. Okay. I'll draw a house like a kindergartner would. So the windows and the doors. Okay. Here you are. And this distance right here is 20 meters. And you've thrown this egg. We're going to neglect the height of the person. Okay, so we're assuming that they're throwing it from ground level. And the egg is going to go in an arc. So here's the egg traveling, and it's going to splat on the house somewhere. And what we want to know is how high up on the house does it hit? What is the delta y when it hits the target? Okay? So the first thing we want to do with any projectile motion problem where the projectile is launched at an angle is we want to take that initial velocity, so 18 meters per second at 50 degrees, and we want to break it up into components, the initial y velocity and the initial x velocity. So we have 18 meters per second at 50 degrees. Okay. Someone is here for the memes. No memes today, Chris. Former student Chris stops by. I don't have any memes today. I will try to add some memes soon. Nice to see you, or nice to hear from you. So what I will do is I will get the vertical component of this velocity as 18 sine of 50 degrees. So that is 13.8 meters per second. And then 18 cosine 18 cosine of 50 degrees is going to be the x component, so that's 11.6 meters per second. All right, so now we plug this into our two equations of projectile motion. We have delta x is going to be 11.6 t, and then delta y is going to be 13.8 t minus 5t squared. So remember, 1/2 g is going to be 5, so because it's 1/2 of 10. That number is only going to change if we do the projectile motion problem on a different planet, okay, or in a different astronomical body. So type it into the live chat if you know what is the mathematical condition that we are going to use to solve this problem. What is the mathematical condition that we're going to use to solve this problem? Because we need, remember, when we're doing a projectile motion problem, we always try to get the time of flight, and then we use that in the other projectile motion equation. So there's, how do we know when the projectile has hit the house? Oh, wait a second. I think I have a lot of delay today. I was noticing that there's about a 30-second delay. So while I'm waiting for someone to type, oh, okay, good. We know the change in x. Excellent. So the delta x is 20 meters. So this is a little bit different from the other problems, because for the other problems we had our delta y equals 0, or our delta y equals negative the height of the cliff, okay? But here we have delta x equals 20 meters. So I would plug in 20 equals 11.6 t. So notice how we're using, yesterday what we did is we used the delta y equation first, or last time we used the delta y equation first. Now we're using the delta x equation first. Divide both sides by 11.6, and we get that the time of flight is 1.7 seconds. Okay? So now what we do is we take that 1.7 seconds and we plug it in for time. So we have delta y equals 13.8 times 1.7 minus 5 times 1.7 squared. And we get about 9 meters is delta y. So that is our answer. So that is how high up the egg will hit the house. Now, what would happen if the house is only 5 meters tall? Type it in the live chat if you know what would happen if the house is only 5 meters tall, or only 6 meters tall, or something like that. All right. So I'm going to start working on the next example here. All right. Yeah, exactly. So someone typed in he missed. So if we compare the height of the egg when it reaches the house to the height of the house, we can see whether it's going to actually hit the house or go over the top of the house. Very good. Excellent interpretation. All right. So let's suppose that you fire a mortar at, let's say, 70 meters per second with angle 45 degrees. All right. And while I'm writing this problem down, if you know the answer, type it into the live chat. What is significant about 45 degrees in terms of the initial velocity triangle? Okay. I don't know why this isn't focusing very well today. You fire a mortar at 70 meters per second with angle 45 degrees from the top of a cliff of height 130 meters. Okay, so let's figure out what that means. Let's draw a picture. Excellent. Yeah. So for a perfect diagonal launch, you have equal x and y components for the initial velocity. Very good. So this problem looks like this. So we've got the cliff is 130 meters high. Okay. We fire the mortar 70 meters per second at 45 degrees. Okay. So it goes like this. All right. And I want to know a couple of things. I want to know how high does it go? What is the maximum height? And I want to know how far does it go? All right. So first things first, I'm going to do my initial velocity triangle. So I have 70 meters per second at 45 degrees. So my vertical component is going to be 70 sine of 45, which is 49.5 meters per second. Okay. And then we're going to have the cosine, 70 cosine is also going to be 49.5 meters per second. Okay? So I don't even have to type it into the calculator because it was 45 degrees. All right? One thing I want to note is that this problem mixes both of these problems. So here we had an angled launch across a level surface. Okay? Here we had a horizontal launch off a cliff. So for this problem, we have an angled launch off a cliff. So this is kind of a mixture of these two problems. Okay, so that's why I do this problem last. Now we get our delta x equation. Our delta x equation is going to be 49.5 t. And our delta y equation is going to be 49.5 t minus 5t squared. Okay? So if we think about it, what is our delta y for this equation? So think back to this problem. How do we solve this problem. We had a certain value for delta y. And what is our delta y going to be in this equation? I will wait. If we consider this to be the final point, what is our delta y going to be? Excellent. Negative 130 meters. That negative is important. So we have negative 130 equals 49.5t minus 5t squared. Okay? So now what I will do is I will add the negative 130. So I'll add 130 to both sides. I get 0 equals 130 plus 49.5t minus 5t squared. And I'm solving for t. All right? So this is a quadratic formula problem, okay? So that's why I do this problem last, because it involves a quadratic formula. So how can you solve that? Well, what I would do, you could do the quadratic formula. That takes quite a bit of time. So I'm going to just use Desmos today. So I have Desmos here, and I'm going to type in our equation. I'm going to type in y equals 130 plus 49.5 t, or x, I should say, minus 5x squared. So I can't put time because Desmos just does y and x. Maybe it will let me do t. Let's see if I do t. Oh, it does let me do t. Okay. So I can see that the graph goes up, but it doesn't come back down. So I'm going to zoom out. So we can see that, and we're trying to figure out, remember, we're trying to figure out when does this function equal 0, okay? So I can see there are two zeros. One of the zeros is right here. That's at negative 2.157 seconds. The time elapsed has to be positive, so we don't use that 0. We would use this 0. And so what that says is that the projectile is in the air for about 12 seconds. Okay? So the time of flight is 12 seconds, which I then plug into my delta x equation. So I have delta x equals 49.5 times 12 equals 594 meters. So that's how far it goes, 594 meters. I know that's hard to see. I apologize. What if we want to figure out how high is it going to go? All right, so let's go back to Desmos. This is the y as a function of t, of the projectile. Zoom out. Okay, this, I'm going to expand the horizontal axis. Let's have the horizontal axis go from minus 20 to plus 20. Okay. And I will go ahead and label the axes. So we have time in seconds, and we have y in meters. Okay, so here's the graph. And we can see that the initial height is 130 meters. So if I want to know how high does the projectile go, I would just go to the apex of the parabola, and I can see that the apex of the parabola is at 252, about 253 meters. So what that tells me is that the maximum height is 253 meters. So we can use Desmos to do all the math for us, okay? Because really physics is about physics. I mean, knowing math is really useful for physics, but this is a physics class, not a math class. So I want you to first and foremost understand how to do the physics. So if you want to use Desmos to find the apex of a parabola or find the zero of a parabola, then go ahead and do it. Okay, so now we're going to move on to the second part of today's lesson, which is motion graphs. Motion graphs in projectile motion. So how can we use motion graphs in projectile motion? Okay, so you might recall that we had velocity time graphs, okay, and the slope of a velocity time graph was acceleration. Okay, so in projectile motion, because the projectile is moving horizontal or moving diagonally, we actually are going to have two velocity time graphs. We're going to have an x velocity versus time graph, and we are going to have a y velocity versus time graph. Okay, so we have two graphs. Now, what do these graphs look like? Well, the x velocity time graph is actually going to be constant. Okay, why is that? This is a flat graph because gravity doesn't cause a horizontal acceleration. So the horizontal velocity remains constant the entire time, okay? The horizontal velocity remains constant the entire time. So whatever value the initial horizontal velocity is, Vx naught, that's going to be the horizontal velocity the entire time, okay? The y velocity is going to be sloped downward, okay? It's going to look like that. Its intercept is going to be the initial y velocity, okay? And the slope is going to be whatever the acceleration due to gravity is. So if we launched this projectile on Earth, this slope will be negative 10 meters per second squared. Okay. If we launched it on another planet, it's going to have a different slope. All right. A couple of things. At the highest point, so you might remember that when we were talking about the chicken wing problem, or the geyser problem, the old faithful geyser problem, at the highest point, the velocity was 0. However, when something is moving diagonally, at the highest point, you might not have that the velocity is 0. But what you will have is at the highest point, the y velocity is equal to 0. Okay, so that is important. At the highest point, the y velocity is 0. So this moment right here, that is the highest point. Okay, let's try to understand that in pictures. If you are launching a projectile like this, so here's the path of the projectile. At the highest point, which is right here, we can see that the velocity is horizontal. Okay? So at the highest point, Vy equals 0. And also at the highest point, the speed is equal to whatever the initial x velocity was. Okay, so we can see that initially we start out with a y component to the velocity, and that y component gets smaller and smaller and smaller until we get to the highest point where there is no y component to the velocity, and all we have is x velocity. Okay, and the x velocity never changes because gravity doesn't accelerate horizontally. So this is kind of an important point. Okay, so let's do a little example just to solidify these concepts. So what if we had a Vy graph in meters per second versus time, and we had a Vx graph in meters per second. And so one of these graphs looks like this. Let's suppose that that is 90 meters per second. This is 4 seconds. Okay, and the Vx graph looks like this. And let's say that it starts out at 20 meters per second. Okay, so I've got a couple of questions for you. First of all, what is Vx naught based on this graph? What is Vy naught based on this graph? What is the acceleration due to gravity based on this graph? And also, what is the time at which the highest point is reached? Okay, so to get the initial x velocity, I would want to go to the x graph. So I would go to the x velocity graph. And the x velocity graph is a horizontal line. And at time 0, I can see that the horizontal velocity is 20 meters per second. Okay, for the initial y velocity, I would go to time 0 in the y velocity graph, and I would see what value the y velocity has. And that is 90 meters per second. What is the acceleration? Well, the acceleration, there is no acceleration in the x direction. All the acceleration is in the y direction. So this would be the slope of the Vy versus time graph. And I can see that this graph goes down 90 and over 4. So the slope is negative 90 over 4, which is negative 22.5. So the acceleration due to gravity is negative 22.5 meters per second squared. And the time at which the highest point is reached is going to be the time at which the y velocity is 0, which would be 4 seconds. Okay, so that is how you analyze motion graphs for projectile motion. All right, so that's my lesson for today. I will go ahead and see you in the Zoom room. All right.